the morning, but maybe we should start the second day. Typhoon is not coming. Passing by. So luckily, typhoon will come to Taipei, so the conference will be going on smoothly. So now we are going to listen to James Liu's lecture on supergravity, and he will continue his talk. Thank you.
Okay, good. So let's see here. So yesterday I tried to give a brief overview of supersymmetry and supergravity, and towards the end I touched upon this idea. If you look at supersymmetric theories in different dimensions, I had a little table starting at 11 dimensions down to 4 dimensions of various amounts of supersymmetries. And I also showed you how 11-dimensional supergravity can be compactified in a circle to construct 2A supergravity in 10 dimensions. And so I hinted at least that you can sort of move up and down in dimensions by compactification or by lifting. And so I'd like to go over that in a little bit more detail today. So the plan for today is to talk about Kaluza-Klein reduction. And so let me just start by setting up the situation a little bit and giving a simple example, which is, let's say I have a higher dimensional theory. I would call it capital D. Sometimes I just call it maybe a higher dimensional theory. I got compactify on an n-dimensional manifold xn, and that gives me a lower dimensional space-time. So I can split the coordinates into sort of lower dimensional x mu coordinates and internal yi coordinates. So there's capital D minus n lower dimensional coordinates. Sometimes I'll just call these space-time for the lower dimensions, and then internal space for the compactified dimensions. And I might call this little d number of coordinates over here, just to set up the notation. So the basic Kaluza-Klein idea is to take a higher dimensional field, which can depend on all coordinates x and y, and split it up into harmonics or modes on your internal space. So depending on the manifold, I can find usually a set of harmonics or Fourier modes, which I call f sub a of y or something like that over here. And then I just have a decomposition in terms of space-time fields over here times internal modes like that. And as long as I expand on a complete set or a complete basis of eigenstates on my internal manifold, I've basically done nothing except just rewrite all my fields in a lower dimensional type of notation. One thing you might think about, of course, is it takes an infinite set of modes to make a complete set. So if I have a finite number of fields in the higher dimensional theory, it expands to an infinite tower, or infinite number of lower dimensional fields as well. I hope this gives some hint also that by expanding on harmonics, or modes in the internal space, somehow this is dependent on the geometry of my internal manifold, and isometries or symmetries of my internal space will show up as symmetries of my lower dimensional theory as well. Let me give a basic example. The original Kaluza-Klein idea, which I'll come back to, is if you take 5-dimensional pure Einstein theory, pure Einstein gravity, and you reduce it on a circle, you end up with Einstein theory plus a gauge theory and a Maxwell theory and a scalar field. So you can get sort of gauge theories or Maxwell theory out of 5-dimensional gravity. This is sort of an idea of unification of sort of gravity and electromagnetism. But let's start simpler and just consider a scalar field in 5 dimensions or in higher dimensions. And so sometimes I'll just say 5 dimensions compactified to 4 just for simplicity. But in general, it's capital D dimensions compactified down to some lower number of dimensions. So a scalar field has this is a free scalar, has a very simple action of Lagrangian, which is basically just d phi squared over here, and I introduce the higher dimensional mass term just for fun. Mass term is completely optional. And this gives you the familiar Klein-Gordon equation, box minus m squared phi equals 0, where this is the higher dimensional box. So the natural thing is to say, if I'm going to compactify this on a circle, let me call my circle dimension y. I'm going to make it a periodic coordinate. And so we can shift y by what I call 2 pi r. This is circumference. You can also call it capital L or something like that. Y goes to y plus 2 pi r periodicity. And as you know, if you solve for modes on a circle, the natural thing to do is to introduce a Fourier decomposition. So I can take my field and decompose it into sort of the lower dimensional field times Fourier modes e to the I n y over r. And you see these functions here are designed to be periodic under the shift symmetry of the circle. And of course, there's an infinite number of Fourier modes. Since I'm using a complex scalar, let me just sum from minus infinity to plus infinity like that. So once I substitute that into the Klein-Gordon equation, then the higher dimensional box goes into the lower dimensional Laplacian plus d by dy squared over here. And if you think of a y derivative acting on your mode over here, it brings in in over r. Since you have a second derivative, it brings in I squared, which is minus sine n over r y squared. This is an infinite set of modes, so I still have an infinite sum over here. So the higher dimensional Klein-Gordon equation is exactly equivalent to that. No more, no less. But once I see this in 4 dimensions, and I realize that these Fourier modes form an orthogonal set, and the only way to solve this equation over here is mode by mode, so that the space-time part over here has to be equal to 0 for every value of n over here. And so I'm left to an infinite number of lower dimensional equations, box minus m squared phi equals 0, where I have the subscript n over here to denote mode n, basically. Then the well-known Kaluza-Klein mass formula over here is the mass of mode n, m squared, is the original mass squared over here, plus this additional term that came from this n over r that came from the y derivative over here. So each mode in the Kaluza-Klein tower has a different mass given by this n over r factor over here. So let me just summarize that picture a little bit. So a single complex scalar in 5 dimensions decomposes into an entire tower of states in 4 dimensions, and they all have potentially different masses, m sub n over here. Actually, the mass of mode plus n and the mass of mode minus n are identical. That is a degeneracy. I can also imagine the Fourier modes e to the I n y over r. That's basically a plane wave mode along a compact or along a circle direction. So this n over r factor can also be represented as internal momentum of motion of the particle along my internal circle. And there's a bit of a geometric picture over here that the momentum or the motion of the particle along the circle corresponds to a conserved charge in 4 dimensions. This is the idea of isometry of my internal space, giving rise to a symmetry in the space-time theory, in the lower dimensional theory. Once I think about momentum in the circle, or I think of charges, and we also have the notion of charge conservation. So we have momentum conservation along the circle, and that corresponds basically to lower dimensional charge conservation. Then I think about each of these modes over here carries some n units of charge. N units of momentum corresponds to n units of charge. So I have a 0 mode phi 0, which is neutral. I have a particle phi 1, which has 1 unit of charge. Phi 2 has 2 units of charge. Phi minus 1 has minus 1 units of charge, and so on. This is an idea of getting some electromagnetism out of a theory without electromagnetism into higher dimensions. Now this might be a sort of a trivial sort of statement, but I want to make the claim that this set of equations of motion in the lower dimensional theory can actually be obtained from a lower dimensional Lagrangian as well. It should be kind of obvious. Box minus m squared, this is a Klein-Gordon equation. So I see a Klein-Gordon equation like this. I should say a Lagrangian should look basically like that. And don't be surprised This looks like the original 5-dimensional Lagrangian, except instead of a 5-dimensional mass over here, this is my lower dimensional Kaluza-Klein mass over here. And of course, I kept the sum because the lower dimensional theory actually has an infinite number of Kaluza-Klein states inside it. So as I said, this notion of charge is that each Kaluza-Klein mode on phi sub n would have charge n. And if you think about charge conservation, if I had an interacting theory, you have two particles, charge 1 and charge 1 that interact with each other. Sorry about that. So if I had two particles of charge 1 and they were allowed to interact, charge conservation says if they join together, they sort of form a particle of charge 2. If a particle of charge 1 and charge 2, they interact, they can form some state with charge 3, and so on. So it's an interesting phenomenon. Now once I include one of these Kaluza-Klein modes with non-zero charge, and if it has interactions, then it should generate or should be able to provide a source for additional modes with more charges as well. So this sort of speaks to the consistency of the theory, that once I've decided to include some modes with charge, then I have to allow all possible interactions with those charges, and then I end up with all possible modes. Now, of course, in a free theory without interactions, you can ignore what I just said, but in realistic theories with interactions, once I bring in a charged state, which means I bring in a state in the Kaluza-Klein tower, then I have to bring them all in for consistency. There's an exception to that. If I only keep the zero mode, which is the one without any internal momentum, that keep the zero mode, zero charge interacting with zero charge gives you zero charge. It forms a sort of subsector of the theory. So it's consistent to have all neutral particles in the theory and just truncate or throw away all the massive particles or all the charged particles as well. So this gives a bit of a dichotomy. There's sort of two ways to view Kaluza-Klein reduction. If I start with my original high dimensional field, if I didn't do anything special, I end up with a Kaluza-Klein tower, which means I have an infinite set of lower dimensional fields, and I keep them all, and it's an interacting theory with a whole bunch of Kaluza-Klein towers. On the other hand, I can do a truncation and start with my original field and keep only the zero mode. And it turns out it's consistent, as I said, to keep only the zero modes, because zero charge will not form sort of zero charge states forms a sort of a subspace all by themselves. Now there's a bit of confusing terminology which I confuse myself, so I apologize in advance. When you speak of Kaluza-Klein reduction, sometimes we talk about Kaluza-Klein with the entire tower. Sometimes I say Kaluza-Klein reduction, and I think of just the zero mode sector as well. So there's a little context involved. However, the notion of consistency is often an important one. I'll come back to that tomorrow as well. I'll say a little bit more today about the notion of a consistent truncation. Is that I gave you two possibilities, because it wouldn't be consistent to keep the zero mode plus one or two charge modes without keeping the entire tower. Once you bring in one state in the Kaluza-Klein tower, basically bring in the whole spectrum. Otherwise, it wouldn't be consistent. So I can make that a little bit more formal, not too formal, but a little bit more, by talking about this idea of a consistent truncation. Why is it consistent to sort of truncate your theory to keep only a subset of states in your whole Kaluza-Klein tower? And the idea here is that if I can reduce myself to just the zero mode sector of the theory, then usually I get a smaller, I don't have to worry about this infinite tower of fields. Often, if there's a mass gap or something that sets the scale of my Kaluza-Klein tower, I could sort of go to a sort of a low energy case where I can ignore the higher dimensional field. And one way to have a consistent truncation is to say, if I'm able to have a subset of fields in lower dimensions, in let's say 4 dimensions, if the 4-dimensional or the lower dimensional equations of motion of my subsector of fields implies the original equations of motion, then I defined truncation to be consistent. So maybe I didn't say that in such a good way. Let me say that again. The idea of a consistent truncation is if I solve my lower dimensional equations of motion, I'm guaranteed to have a solution to the original higher dimensional theory. I don't need any additional constraints. I don't need to worry about some energy considerations of, well, I don't excite higher energy states. It's just that by solving the lower dimensional equations of motion, you automatically solve the higher dimensions. So that's the idea of a consistent truncation. So in this model at hand, the Kaluza-Klein scalar, if I go to the zero mode over here, then the lower dimensional equation, the zero mode, this was the five-dimensional mass, but the zero mode mass is just the original mass. And so my lower dimensional equation of motion, my lower dimensional Laplacian over here, since the zero mode is independent of y, lower dimensional Laplacian basically is going to be the same as the higher dimensional Laplacian, which means my lower dimensional equation of motion, in a very trivial manner, just gives rise to the same higher dimensional equation, like that. Now this is a bit of a, seems like a bit of a simple exercise for a simple circle reduction. However, this notion of consistency, lower dimensional equation implying higher dimensional equation, is highly non-trivial in a lot of more sophisticated constructions like the sphere reductions. Now, one way to get a consistent truncation is this charge conservation idea. If I go to a charge neutral sector, all my interactions between charge neutral particles sort of form a subgroup by themselves. They cannot provide sources for any charged states. So I can always get a consistent truncation by restricting to sort of charge zero particles. Charge zero in a circle is an obvious statement, but if I generalize that statement to an arbitrary compactification and an arbitrary internal manifold, the charge neutral idea basically means singlets under your isometry group. So anytime you truncate the singlets under the isometry group of your internal manifold, you're guaranteed to have a consistent truncation.
We keep all the modes with n equal to like multiples of 3, then over interaction we still would only get charges of multiples of 3. Would that be also a...
That is actually also a consistent truncation. That's a very interesting case. Sorry, having microphone issues. But absolutely. Another way to think about that is if I define something like a charge mod 3 as a new version of charge, a charge mod 3, then I truncate to sort of neutral particles under charge mod 3. I've done a similar sort of thing. I've gone to some singlet states or neutral states under a more generalized notion of charge. And so these would be sort of like a Z3 orbifold or something of that nature as well. So that's a good point. You can be a little bit more clever like that. But usually underlying that is still this notion of some version of charge neutrality. Good. So that's sort of an overview of Kaluza-Klein theory done on a scalar field. But let me come back to the idea of Kaluza and Klein. If you take a 5-dimensional Einstein gravity and reduce a circle, you can get Einstein-Maxwell scalar theory, which basically means, let's do Kaluza-Klein for gravity. And, well, there's complications, of course, is I start with my higher dimensional Einstein-Hilbert action. That gives the standard Einstein equation. In fact, since I didn't have any matter fields over here, it gives me the vacuum Einstein equation, which I can write either in the Einstein tensor or the Ricci form like that. Now, I can do a Kaluza-Klein reduction just like the way I did it for a scalar field. I decompose into Fourier modes on a circle. E to the I n y over r modes on the circle. Except there are a few complications to worry about. One thing is kind of obvious, is now I have a tensor field, GMN over here. My capital letters are the higher dimensional or the 5-dimensional indices, mu nu are the 4-dimensional indices, y is the 5th dimension. Yeah. And so I have to pay attention to the decomposition of my tensor indices. My higher dimensional metric can give me a lower dimensional metric. It can give me a off-diagonal G mu y term over here. You probably already know the punchline of this statement over here. From a four-dimensional perspective, mu is a vector index, y is an internal index, which doesn't transform under four-dimensional Lorentz symmetries. So this looks like a four-dimensional vector, and GYY looks like a scalar. So a graviton, in 5 dimensions, looks like a four-dimensional graviton, four-dimensional vector field, and a four-dimensional scalar. And that's how you can get electromagnetism or U1 symmetry out of Kaluza-Klein gravity. However, that's not quite as simple as that, because you have a lot of gauge symmetry, or you have general covariance, and that has to be taken into account as well. So it's like what was mentioned in some of the talks yesterday. A four-dimensional symmetric 4x4 matrix has 10 independent components. Once you hit it with the gauge symmetries for a massless graviton, you reduce it to 2 felicity states, or 2 physical states. In 5 dimensions, over here, you have 15 components, and they get reduced as well. And we'll take a look at that very briefly. The other point I want to mention, of course, is that the Einstein equation is nonlinear, whereas the scalar field example, the Klein-Gordon equation, was a very simple linear equation. It was kind of obvious. The nonlinear reduction is a little bit more complicated. So the first thing you could do is the professor told me many years ago when I was in school, B-wise, linearize. Not the complete story, but we can work out the linearized Kaluza-Klein spectrum without too much difficulty, and usually that's a very good starting place. So let me remind you of the linearized Einstein equation, which is, well, whatever dimension you're in, it's box h bar. Well, in Lorentz gauge, it's box h bar equals 0 with a Lorentz gauge or harmonic gauge condition like that, where I didn't actually write down h bar. That's the so-called trace reversed HMN field. So I want to think about this as a 5-dimensional equation. I want to reduce this down to 4 dimensions using my Fourier modes on the circle. Yes?
Well, brief question. GM is G large MN is a metric.
This is a metric, right?
And G mu is also metric,
Right.
and GYY is also metric. But G mu y is not metric, but it's more connection.
I would call G mu y still a metric.
It's still a
It's
metric.
an off-diagonal part of the 5-dimensional metric.
And from the four-dimensional point of view, G mu y is a connection, right?
It's not a connection in the sense of parallel transport. Or another way to think about it is if I have a Christoffel connection, that's sort of a derivative of a metric. And these are not derivatives. So I wouldn't necessarily call these connections. But maybe another way to say it is if I do linearized gravity, I expand the 5-dimensional metric, or any metric, as eta mu nu plus h mu nu. I call this G. But in reality, I can use h over here for linearized gravity. And so I have h mu nu, h mu y, and h y y. Those are all tensor fluctuations of some sort. Yes?
So if we consider Gibbons-Hawking term.
Gibbons-Hawking term.
Yes. So how do we deal with that in a compactification?
The Gibbons-Hawking term is a surface term. And so if we do actually want to have a good variational principle, I will have to add, so this is the Einstein-Hilbert term. You're absolutely correct. I would add a Gibbons-Hawking. However, for a compactification on a circle or an actual compact manifold, there's no boundary over here. So a Gibbons-Hawking term really is a boundary type term. And so the 5-dimensional, so normally one way to ignore the Gibbons-Hawking term in sort of flat space at least, is imagine you push the boundary to infinity. Fields die away fast enough at infinity, you go to asymptotically Minkowski space, and you can ignore that. It's not exactly true if you have something like ADS or non-trivial space, or if you chop off your boundary where the fields haven't died off fast enough. However, even ignoring all those considerations, if you're compactifying in a circle, the Gibbons-Hawking term still exists, but the Gibbons-Hawking term is at the boundary of four-dimensional space-time, not anything to do with the circle direction. So the compactification part, or the Fourier modes on a circle, is unaffected by the Gibbons-Hawking term. But you're absolutely right. In that point of view, the five-dimensional Gibbons-Hawking term will reduce to a four-dimensional Gibbons-Hawking term as well.
Tmn is the energy momentum tensor in d dimensions.
That's right.
And T mu nu is the energy momentum tensor in 4 dimensions. What about Tyy?
Y is, well, it's internal pressure or something like that. To be honest, I'm not sure exactly what I would call it in 4 dimensions.
Maybe we may talk.
Yeah, we can talk about that later. But at least for this setup over here, I've done vacuum Einstein equations, so there's no stress energy tensor. But absolutely, if I had a more complicated theory, I would have a 5-dimensional stress energy tensor. There is a Tyy component. I will try to show that even the 5-dimensional vacuum Einstein equation, I will have an effective 4-dimensional stress energy tensor coming out from components of, well, internal components of the metric. Good. Well, let's take a look at these linearized Einstein equations. Since I'm compactifying in a circle, everything is usually fairly easy. Let's go ahead and just do that. So just like in the scalar field case, I'll take my metric fluctuations. They can depend on all coordinates, including the internal coordinate y, and decompose them into Fourier modes, e to I n y over r, just like a scalar field. Only thing different from the scalar field equation is our capital Mn tensor indices over here. So the fun thing about harmonic gauge is the Einstein equation looks just like a Klein-Gordon equation over here, box minus m squared, Hmn equals 0. This is the Kaluza-Klein mass. Just like in the scalar field case, Kaluza-Klein mass. There is no 5-dimensional mass for a graviton. I'm doing ordinary 5-dimensional Einstein-Hilbert theory for 5 dimensions. But nevertheless, when you reduce on a circle, you get Kaluza-Klein masses, just like that. Now, where it gets a little bit more complicated is the harmonic gauge condition, which is this one over here. dm h bar mn equals 0. This is a capital M. It's a 5-dimensional derivative, which I can break into 4-dimensional derivative plus an internal y derivative. And y derivative, acting on the Fourier mode, brings in a factor in over r, which is just I times the mass over here, which means the harmonic gauge condition, when I break it up into 4-dimensional indices, looks something like that. It's basically the 4-dimensional divergence plus a 5th-dimensional mass term equals 0. And I did a further decomposition just to really bring things into the 4-dimensional point of view, where I have a 4-dimensional index nu over here, or a 5-dimensional index y, like that. Now, this is interesting, because when I see these equations, this h y nu over here enters without a derivative. So if I divided this by I m over here, I can solve this equation for h bar y nu. I can solve this for the off-diagonal h bar metric over here. Likewise, I can solve this for h bar y y. The exception to that, of course, is if I don't want to divide by 0. If I have the 0 mode, n equals 0, then these mass terms disappear, and the case is slightly different. So I'm going to consider 2 cases, 0 mode and non-zero mode. Let's start with the 0 mode, or the 0 mass case. Kaluza-Klein n equals 0. Then it's very simple. There's no mass term over here, because it's the 0 mode. So the 4-dimensional Einstein equation is basically box h bar equals 0. And then the gauge conditions have 2 of them. There's this guy over here, d mu h bar mu nu equals 0. And then there's this guy, d mu h bar mu y equals 0. There's a slight complication. This is the